Now we are going to discuss oblique incidence. What is the oblique incidence? How it is different from the normal incidence? And again, we'll see different situation of the reflection and refraction. And later we'll see that what is going to happen in case of parallel polarization and perpendicular polarization. What will be the situation of the parallel polarization? There we will try to find at the angle that is called as the Brewster angle, and later we'll have discussion about critical angle also. And when we'll proceed one by one, so we have multiple equations for the electric field as well as magnetic field. With the help of that, we are going to discuss reflection and refraction of plane wave at oblique incidence. As you know that reflection means that wave is going to reflected in the same medium. Refraction, wave is going to travel in the another medium. Okay. So let's start this topic. Today's topic of this lecture is reflection and refraction of plane wave at oblique incidence. If you still didn't subscribe our channel, please subscribe it, share with your friends. Okay. So now here what we are going to see that if wave is going to strike the surface at any angle apart from the 90 degree, then we call as the oblique incidence. Okay. So that angle is apart from the 90 degree. So here we have time dependent fields. So that time dependent fields is represented with the help of K and R here. So first equation we have equal to E naught e to the power j into KR in minus omega t. Whereas magnetic field is H naught e to the power j of KR minus omega t. So this K is here, that is called as the propagation vector, or it is also called as the wave number vector. So that's K is given as Kx Ax plus Ky Ay plus Kz Az in 3 dimension, and R is called as the radius vector, which is given as X Ax plus Y Ay plus Z Az. So in case of when we'll talk about the informed plane wave, so that informed plane wave we can write it is function of R and T. So E of R comma T E naught cos KR minus omega T. So this is the real part. So that can be also be written as real part of E naught e to the power j inside the bracket KR minus omega T. Since we have e to the power I theta equal to cos theta plus j sin theta. Okay. So on the basis of that, this cos theta is going to give us the real part. That's why we are using the RE. And this magnitude of the K is related to the omega as a dispersion relation. So later we'll see that K also can be same as the beta. Okay. So that is the phase constant. So here finally K square equal to Kx square plus Ky square plus Kz square. That is equal to omega square mu epsilon. And in case of lossless medium, K is same as the beta. So this propagation vector will become same as the phase constant. So that Maxwell equation for source free region, okay, for the source free region is given as K cross E equal to omega mu H, K cross H equal to minus omega mu E, and K dot H equal to 0 and K dot E equal to 0. So if you're able to remember earlier expression, so there you have in terms of like we have del cross E equal to minus dou B by dou T. And you have del cross H equal to that is J plus dou D by dou T. So it is the source free region. So this J value is going to be 0. That is the conduction density actually. That is the current density. That is the conduction current density J here. And earlier we have del dot B equal to 0 and we have del dot D equal to rho V, and this is the source free region, so charge is also not available, so that is going to become 0. So here wherever del is there, that del is replaced by the K, and as per the condition we have this equation number 5. Now from here equation number 5 we can conclude that E and H, E, H and K, all three are mutually orthogonal. So these three factors are perpendicular of each other. Already we know that in case of when we'll talk about transverse EM wave, so there we have E and H is already perpendicular to each other in the direction and perpendicular to the direction of propagation. So here EHK, all three are the mutually orthogonal, and E and H lie on the plane. So that is defined here, K dot R equal to, so finally that dot product here, so we have K suffix X into X, K suffix Y into Y plus K suffix Z into Z. So this is going to be the constant. Now we are going to utilize the equation 3 and 5 to obtain the H field. So that H field is given as H equal to 1 by omega mu into K cross E. So this also can be written as AK cross E by eta. So this expression already we have earlier for the eta, how we are able to write. So now here we are going to consider the situation of the oblique incidence. So that wave is going to strike the surface, that plane of the wave is going to strike the surface at any angle apart from the 90-degree, that is called as the oblique incidence. So finally here propagation vector K is going to strike the surface with angle theta I, and here that is being reflected with angle theta R, and after refraction in the medium 2, it is going to make the angle theta T. So that is represented here by KT, in reflection KR, and KI is the incident. Since it is being transmitted from one medium to another medium, so it is KT, and here we have unit normal vector, that is the AN. Okay, this is the unit normal vector. So here boundary condition also later we are going to consider. Okay, so that plane defined by the propagation vector K and by the help of unit normal vector, that is the AN. So this boundary is called as plane of incidence. So this theta is between the K and the normal unit vector. So that is the angle of incidence in medium 1. This is the incident wave, and again it is being reflected. So that is the reflected wave, that is the KR. And in case of medium 2, we have transmitted wave, or that we also can call as the reflected wave. So finally in the medium 1, we have incident wave and reflected wave, and in medium 2, we have only transmitted wave. So how we can write those equations? So for that we are going to consider. So let's EI equal to EIO cos. So similarly what we have earlier, K R minus omega T. So already we got the product of KR. So that we are going to utilize here. So this is for incident. So we have I as the suffix here, KIX into X plus KIY into Y plus KIZ into Z minus omega I into T. Similarly, for the reflected wave, only suffix R, I is going to change by R. Again, in case of transmitted wave, suffix I is going to change by the T. So that is the equation number 7. Now this is going to incident on the boundary with angle theta I, and we have seen that in case of lossless dielectric, this K is same as the beta. So that's why here in case of medium 1, we have incident vector Ki, so that's the beta 1, and finally it's a vector along the different directions. If you're going to resolve this vector Ki, so along the z-axis we have beta 1 cos theta I, along the x-axis we have beta 1 sin theta I. Similarly for the reflected wave, okay, we have beta 1 sin theta along the x-axis, and here beta 1 cos theta r, that is along the negative z-axis. And in case of medium 2, we have K T Z, that is beta 2 cos theta T. So this is the medium 2. So that's why here it is taken as the beta 2. And along the x-axis, we have beta 2 sin theta T. So with the help of this three vectors, Ki, Kr, and Kt, we are going to write the remaining expression. And we know that tangential component of the electric field must be continuous at the boundary. Already we have separate lecture for the electrostatic boundary condition as well as magnetostatic boundary condition in the playlist. You can see that. So this at boundary condition, at boundary, these tangential components are continuous. Okay. If you have any doubts, you can write in the comments. Okay. So now so finally at the boundary means here we have taken at z equal to 0 as the interface or boundary. So that this tangential component, so in the medium one we have EI, ER. So this sum of these two, EI plus ER, and in the medium two we have ET. So that is ET, so z equal to 0 at the boundary condition. So this boundary condition can you satisfy the waves for all value of x and y. So what is the condition for that? If omega I equal to omega r equal to omega t, all three are equal. Similarly, kix equal to krx, ktx equal to ks, and kiy equal to kry equal to kty equal to ky. So if these three conditions are satisfied, okay, then we can utilize these boundary conditions. So this condition 1 implies that frequency is unchanged since incident, reflected, and transmitted, all values going to be omega, and omega is what? 2 pi f. So it shows that frequency is unchanged. Whereas this equation 2 and 3 says that this tangential component of the propagation vector be continuous. So for that, phase matching condition is there, and this Ki, Kr, Kt must lie in the plane of incidence. Okay. So that plane of incidence in the same propagation vector are going to lie. So by this condition, 2 and 3 will have Ki sin theta I equal to Kr sin theta R. So both are going to lie in the same plane. And similarly, we'll have Ki sin theta I equal to Kt sin theta T. So here theta I is the angle of incident, theta R is the angle of reflection, and theta T is the angle of transmission or refracted angle. Okay. So in case of lossless medium, already we have seen that this propagation vector is going to be equal to the beta. Okay. So beta 1 equal to omega root under mu 1 epsilon 1. So in case of lossless medium, we have value of this sigma is what? 0. Conductivity is what? 0. So again in the medium 2, Kt equal to beta 2 equal to omega root under mu 2 epsilon 2. So that means here both medium we are considering as the lossless dielectric medium. So from this equation 9 and 10, 11, what we can say that theta I equal to theta R. Okay, since Ki and Kr both are becoming equal, then we'll have sine theta equal to sine theta r. So when sine value will be equal, if angles are same. So that's why here we have theta I equal to theta r. Now by using equation 10, 11 and 12, okay, we have sine theta t by sine theta I equal to Ki by Kt, and this is the u by u2 by u1. Okay, this is the u2 by u1 equal to root under mu1 sigma 1 divided by mu2 sigma 2. This is also called as the Snell's law, where u is the omega by k. This is known as the phase velocity. So this equation 14 is also known as the Snell's law. So which can be written as n1 sine theta I equal to n2 sine theta t, where n1, n2 is the, okay, so that value here sine theta I. So finally n1 is c root under mu1 epsilon 1, that can be written as c by u1, and this n2 is c root under mu2 epsilon 2, that can be written as c by u2. So these are the refractive index of that medium. N1, N2 both are the refractive index. It's not eta, okay? So now this is the general discussion about the oblique incidence. Now we are going to take the condition when it will have parallel polarization and later we'll have perpendicular polarization. So till now if you have any doubt, you can write in the comment. So when it will be said to be parallel polarizations. Polarization already we know that it is the orientation. Okay. So on the basis of that, previously we have discussion about elliptical, circular, linear polarization. So when we say that it is the parallel polarized wave, if E's electric field component is parallel to the plane of incidence. What is the condition? Electric field should be parallel to the plane of incidence. So finally here, this medium 1 having mu1, epsilon 1, medium 2 having mu2, epsilon 2 parameters, and this Ki is the incident vector. So it has now magnetic field components is perpendicular to this plane of wave, and this dot shows that it is coming out from the surface, and Ei is the parallel to the plane of incidence. After reflection, direction of HR is going to change. That is the magnetic field component direction has changed. Earlier it was coming out from the surface, so it is now again perpendicular, but direction has changed. If here it is the AY, here it will become the minus AY. But EI remain along the X direction only. Okay, after reflection also. And in case of transmitted wave, that magnetic field component remain along the y-axis and electric field component remain along the x-axis. So electric field component is always parallel to the plane of incidence. Then it is the condition of parallel polarization. So this electric field is going to lies in the xz plane, since we are considering here that that wave is going to propagate along the z-axis, and that's plane of wave incidence, that is the xz plane here. So it is the condition for the parallel polarization. If electric field is going to lie in the xz plane, and it is a condition of the parallel polarization. So now we'll have expression for the electric field and magnetic field. So we know that in case of medium 1, we have incident wave and reflected wave. So we have expression for the electric field component here, that is EIO cos theta I AX minus sin theta I AZ e to the power minus j beta 1 x sin theta I plus z cos theta I. So again this one we are going to like if you'll consider the situation, so where how these electric fields are parallel, perpendicular magnetic field. On the basis of that, this so when we are going to resolve this expression, we are going to obtain. Suppose, for example, if you have condition like this, okay, and this is the Ki, this angle is theta I. So finally, here if you draw another line, so this angle also is going to be what? Theta I. And if you have perpendicular values here, so in that situation, now if electric field is what? It is the perpendicular here. Okay. So in that case, we'll have another diagram. So this angle is what here? This is the interface, or we can go to the previous diagram. So in this here, what is happening? It is in the plane, same plane it is there. Okay. So it is parallel to the plane of wave. So now here we can have another line if you draw. So this is at what here? Theta I. Now this is the theta I. So finally here we'll have this value will be how much? If it is perpendicular to this, it is actually parallel to this plane of wave. So better we can see for the magnetic field, or you can resolve this. So in that condition, if this vector is going to look like this, okay, electric field. So this angle is theta I. So this angle also going to be the theta I. So this angle will be what? 90 minus theta I. And this is the electric field EI. So this can be written again along the, on this again you can make another, this will be the how much? Theta. So this is the vector EI cos theta I, and here we'll get what? EI sin theta. So on the basis of this, we are able to write this expression. So this electric field components, this is along the x-axis, and this one is along the, that two components are there, cos theta Ix and sin theta I Az. Similarly, for the magnetic field, so this magnetic field, we can write here HIO, but in already we know that the relation between E and H, this is equal to eta. So on the basis of that, magnetic field H can be written as E by eta. So in the medium one, it is EIU by eta 1. So e to the power minus j beta 1 cos, inside the bracket we have x sin theta I plus z cos theta I EY. So this component is along magnetic field is what? Along the y-axis. Similarly, in case of reflected wave, what is going to happen now? Z was the positive earlier, is going to become negative now. So that's why here we'll have sign is the plus. Okay, when we'll try to find the resultant of that, and this Z is changed with minus, so that sign is here minus. Similarly, in case of reflected wave, already we know that direction of the magnetic field is going to change. If earlier it is along the positive y-axis, now it will be along the negative y-axis. That's why we're getting the sign negative here outside. And this plus sign become the negative, since wave is going to, now direction has changed from the positive Z to negative Z. And beta 1 is what? Omega root under mu1 epsilon 1 in case of lossless medium. And in medium 2, what we have? In medium 2, we have only transmitted wave. So again, since electric field is parallel to the plane of wave, so similar situation is here. ETO cos theta AX minus sin theta T AZ, and e to the power minus j beta 2 for the medium 2 into x sin theta T plus Z cos theta T. So this wave, if you see that the equation is same as the incident wave, only here beta 2 came, and in place of theta I, we have theta T. And this magnetic field remain in the same orientation along the y-axis. So finally we have ETO by eta 2 due to the medium 2, and e to the power minus j beta 2 into x sin theta T plus Z cos theta T into AY. And this phase constant beta 2 is omega root under mu 2 and epsilon 2. So now theta I equal to theta that we have seen earlier, and tangential component of E and H both are continuous where at the boundary we have considered as the Z equal to 0. So we have expression, this is for the medium 1 tangential component, and this is for the medium 2. So we have EIO plus ERO cos theta I equal to ETO cos theta T. Whereas in case of in case of magnetic field, we'll have HIO. Okay. So this HIO minus HRO will be equal to H2. So this magnetic field is written in terms of electric field. So now, how we have done in the normal incidence, in the same way, we'll try to eliminate one component here. Okay, so since we know that reflection coefficient is what? It is the ratio of the ERO by EI, reflected component divided by incident components. So here we are trying to eliminate the ETO value, okay, of the equation 18. So on the basis of that, we are getting eta 2 cos theta t minus eta 1 cos theta I divided by eta 2 cos theta t plus eta 1 cos theta I. So here you have to solve the equation 18 same as the how we are trying to solve the linear equation of two variables. So by multiplying by some coefficient, we are trying to make the coefficient equal. Then by addition or subtraction, we are trying to eliminate one term. So finally, this is the deflection coefficient. So again, for the transmission coefficient, it is the ratio of ETO by EI. So now we'll try to eliminate from the equation 18, we'll try to eliminate the ERO. So like this, we have to multiply. So this top parallel for the parallel polarization, we have 2 eta 2 cos theta I by eta 2 cos theta t plus eta 1 cos theta I. So finally, after rearrangement, we can write like this. So this equation 19 and equation 20, that is the reflection coefficient and transmission coefficient. It is also called as the Fresnel's equation. So this Fresnel equations, now here we have situation of the parallel polarization. Now this thing we can see in the form of the Snell's law. So that cos theta t. So we know about cos square theta plus sine square theta, that is equal to 1. On the basis of that, we have cos square theta equal to 1 minus sine square theta. So cos theta is the root under 1 minus sine square theta. So here we are considering that it is the situation is going to be similar to the reflection and transmission coefficient of the normal incidence if theta I and theta t both are equal to 0. Okay, then it will be same as the previous condition of the normal incidence. That for that separate lecture is available, you can see that. So finally, by using equation 19 and 20, we have 1 plus reflection coefficient in parallel polarization equal to transmission coefficient in parallel polarization into cos theta t by cos theta I. Now here very important concept we are going to define, that is the call as the Brewster angle. So this is also known as the polarizing angle. So it is very important. Okay. So this reflection coefficient numerator, what we have seen that it has negative sign. So it can be equal to 0. So when it will be equal to 0, numerator will be equal to 0, then reflection coefficient will become equal to 0. It shows that there is no reflected wave. So the incident angle, so it is the angle at which there is no reflection takes place in the medium 1. So that is called as the Brewster angle. So that means only transmitted waves are there. There is no reflection. So that incident angle is such that there is no reflection, only we have transmitted wave. So it is also called as the polarizing angle. Why it is called as the polarizing angle? Since arbitrary polarized incident wave will be reflected with only component of E perpendicular to the plane of incidence. So this due to this Brewster effect, where we are going to utilize. So in case of laser tube to control the polarization of the emitted wave. What is the laser? It is the light amplification by stimulated emission of radiation. So there we have use of the Brewster angle. So now here what we got, this is the condition for this angle reflection coefficient going to be 0. So that numerator what we have earlier, eta 2 cos theta t minus eta 1 cos theta I. So this angle of incident become now here Brewster angle. So theta b, it is happening in case of parallel polarization. So we are writing here parallel. So finally it is going to be equal to 0. Since reflection coefficient if it is going to be 0. After that same situation, cos we are writing in terms of sine. So that is the root under 1 minus sine square theta. So after that this rearrangement, we are able to find the sine square theta b parallel. So this expression is 1 minus mu 2 epsilon 1 divided by mu 1 epsilon 2 divided by 1 minus mu 1, 1 minus epsilon 1 divided by epsilon 2 square. So now in equation 23, we are going to apply some condition so that further we can simplify this. So if it is the dielectric lossless medium, okay, and as well as non-magnetic, so in that case, mu1, mu2 is going to become equal to mu naught. So this equation 23 will be in this format. So how we are going to get this? If you'll have rearrangement there, So we have sine square theta b parallel. So finally, if you substitute the value, so we'll have 1 minus mu naught epsilon 1 divided by mu naught epsilon 2. So this epsilon naught, sorry, mu naught will be cancelled. And here, after rearrangement, we can have 1 minus epsilon 1 square by epsilon 2 square. Now again, rearrange this part of, okay, numerators, we have epsilon 2 minus epsilon 1 divided by or we can keep like this only, so that this can be written here in the format 1 minus epsilon 1 by epsilon 2, and denominator can be written as a square minus b square. So we'll have a plus b into a minus b. So here what will happen? This 2 is going to be cancelled. So finally we have this for 1 by 1 plus epsilon 1 by epsilon 2. So if we take a square root this sides, that is sine theta b parallel. So now we have value for this sine. So we can find the value of 10. That is the root under epsilon 2 by epsilon 1 equal to n2 by n1, where this n and n2 is what? This is the refractive index. Now we have another situation, that is the perpendicular polarization. So in case of perpendicular polarization, electric field component will be perpendicular to the plane of incidence. In case of parallel polarization, it was parallel to the plane of incidence. In case of perpendicular, it is the perpendicular to the plane of incidence. So electric field is perpendicular, that means magnetic field will be parallel to the plane of incidence. On the basis of that here, Ki is the incident propagation vector, Kr is the reflected, and your electric field component is perpendicular to the plane of incidence. So it is the dot sign. So here incident, reflected and transmitted, everywhere direction of the electric field component is the same. Okay. And magnetic field is the parallel to the plane of wave here. So this is the Hi here, this is Hr, Ht. Okay. So finally, now this electric field, for the condition of the parallel polarization, electric field must be perpendicular to the plane of incidence. So that is considered your x-z plane. So how we have written equation earlier in case of parallel polarization, in the same situation is going to come here. Okay. So what was the there for electric field, that is going to become here magnetic field, little bit negative sign will change. So finally, EIS, in case of medium 1, we have incident wave, reflected wave. So EIO into e to power minus j beta 1 x sine theta I plus z cos theta I AY. Okay, this is the along the y direction. So incident magnetic field EIO by eta 1 minus cos theta I x plus sine theta I AZ, and these things we are going to obtain. So again, if you see that how we are getting these two factors, so for that we can consider the situation like here we have this is the theta I, we can have this is the theta I, okay, and this is the here Hi. So finally this angle will be how much? 90 minus theta I. And if you'll have perpendicular of this is going to be the theta. So finally this will become Hi cos theta I. Okay. And this one is going to become Hi, okay, Hi sine theta I. So what we are seeing that this Hi sine theta is along the z axis, whereas Hi cos theta is along the negative x-axis. So that's why here, as per that, sign is going to be changed here. We have minus here, cos theta ix, sin theta az, okay, and it is traveling along the z-axis. So that's why plus sign is here. And in case of reflected wave, that is again, z is going to become negative. So that's why it is minus here. Okay, earlier plus, minus. And similarly, you have to resolve this reflected wave components. So here both are positive. Okay, cos along the x-axis as well as z-axis. And after reflection, this plus z become the minus z. In case of medium 2, we have only transmitted wave. So transmitted wave again, we have in place of beta 1, we are going to write beta 2, and electric field components remain along the y-axis, and magnetic field components, same resolution we have. Here it is along the negative x-axis, this is along the positive z-axis, and this exponential is j beta 2 x sine theta t plus z cos theta t. So again, previous situation, theta I equal to theta, and at the boundary tangential component should be continuous. So we have EI plus ERO equal to ETO, and this is for the second, this is for the magnetic field in terms of electric field. So we have 1 by eta 1 inside the bracket EIO minus ERO into cos theta I equal to 1 by eta 2 ETO cos theta T. So from these two equations, we have to find the reflection coefficient and transmission coefficient. So same thing, how we are solving the linear equation of two variables. We have to equate the coefficient by multiplying some numbers. So here it is the 1 by eta 2. By that you need to multiply. And here we have to multiply with cos theta t also. So finally, after rearranging the equations 27, we have eta 2 cos theta I minus eta 1 cos theta t divided by eta 2 cos theta I plus eta 1 cos theta t. So in case of normal, in case of parallel polarization, we have seen that here it was theta t and it was here theta I. So that be careful here. It has interchange here. After rearrangement, you will find. And transmission coefficient 2 eta 2 cos theta I divided by eta 2 cos theta I plus eta 1 cos theta t. So these two equation again, 28, 29, that is the reflection coefficient and transmission coefficient is called as Fresnel's equation of the parallel polarization. So here we have already we have seen that 1 plus reflection coefficient equal to transmission coefficient. If reflection coefficient is going to be 0, then the reflection transmission coefficient is going to be 1. That is, no reflection takes place. So again, numerator is going to be equated to 0. So on the basis of that, we are able to obtain this relation. And again, by using Snell's law, similar process. Okay. And now we'll consider the non-magnetic media. So mu1, mu2 equal to mu naught. And here, if you see that, here what will happen here? This value will become 1. So 1 minus 1 is the 0 here. So that's why this sine square theta is going to be infinity. So this is not possible here, since we know that sine value is between 0 to 1 only. So this Brewster angle is not going to exist in case of perpendicular polarization when we are going to consider the non-magnetic media. Now, if you are going to consider that mu1 and mu2 both are not equal, but epsilon 1 and epsilon 2 are equal, then equation 31 can be reduced in this form. So now here we have Brewster angle is going to exist in this situation, but this is the rare condition. Okay. So Brewster angle is important in case of parallel polarization. Now next is the critical angle and total internal reflection. So like in case of, we have seen in Brewster angle, okay, no reflection takes place. Here it is opposite of that. And by Snell's law, we know that n1 sine theta equal to n2 theta t here. So n1, n2 is the refractive index. So that critical angle is defined as the angle of incident at which total internal reflection occurs. So total internal reflection occurs where, that means if wave is going to incident like this, then finally it will have this portion. Okay, so this theta t is going to be equal to 0. And this is the theta I that will become equal to theta c. So finally, sine 90 value is how much? Sine 90 value is 1. Okay, so that's why here this expression theta I will become theta c. So we have sine theta c equal to n2 by n1. So theta c equal to sine inverse n2 by n1. So this is the valid if n1 is greater than n2. That means reflective index of medium 1 is greater than refractive index of medium 2. So this is the diagram in case of total internal reflection. Okay. So that theta C, theta is becoming theta C here, and this transmitted angle become the 90 degree. So these are the discussion about oblique incidence along with the parallel polarization and perpendicular polarization. And here we have Brewster angle as well as critical angle. So parallel polarization means electric field component is parallel to the plane of incidence. Perpendicular polarization means electric field component is the perpendicular to the plane of incidence. So any doubt is there, you like in the write in the comments, okay? And subscribes and like and share with your friends. Thank you very much.